So just to get started, just give you a quick 20-second background. Breathe Easy is an indoor air quality solutions company. Our motto is making a difference in people's health and well-being. It started off as a social cause to help people breathe clean air and realize that indoor air quality can become into a business as well, a self-sustaining business, more than just a profit-making business. But we are also very passionate about trying to fix the outdoor air pollution. Today's topic, however, is about indoor air quality and from the Indian context perspective. So Hanu did an excellent job in telling us about various technologies and a couple of case studies in Finland. But just to bring it into context, we in India face a much, much graver problem with regards to air pollution as many of the Western countries who take this issue very seriously. And this is something I want to really stress upon in our call today because it's something that resonates with me a lot, and that's one of the reasons I moved back to India and I stayed on in India is to help people breathe cleaner air. If you take a look at this chart, this is a chart from the IQS statistics on air pollution, specifically PM 2.5 pollution. You can see that there's a band of red across the equator, starting from the western part of Africa all the way to Eastern Asia. If you look at Europe, and Hanu, you're in the northern parts of Europe where it's fairly green or light shades of light green, relatively speaking, the air over there is much better. Yet, what I want to impress upon the audience today is that the topic of indoor air quality is taken very seriously because even at low exposure levels of particulate matter and gases, it has a huge health impact on the population. So, and another statistics that I would like to bring to the table over here is how last year the World Health Organization changed their guidelines from exposures of 10 micrograms per cubic meter for annual average exposure. They said, if we can reduce that down to 5 micrograms per cubic meter per person, we will cut over, I can't remember the exact number, but it was over 100,000 lives would be saved if our exposure would go down from 10 to 5. Shortly after that, the US EPA, the Environmental Protection Agency, changed their guidelines and changed their AQI parameters. Earlier, the AQI in the US used to go from 0 to 50 for PM 2.5 corresponding to 0 to 12 micrograms per cubic meter. And they changed that and said now 0 to 50 will correspond to 0 to 9 micrograms per cubic meter. Just a 3 microgram difference from what used to be called good is no longer good. It's moderate now. And now a reduction in 3 micrograms makes they claim in the United States will save over 18,000 lives. So that is the impact of air quality that we're dealing with. In India and many other parts of the world, like some parts of Africa and many parts of Asia, we are breathing air which is over 100 micrograms per cubic meter. And for certain days in the year, even over 500 and even 1,000 micrograms per cubic meter. A huge problem that we need to take cognizance of. So it's not just the Asian countries, but 90% of the world population breathes air that exceeds the WHO targets on particulate matter. And what I just mentioned earlier, the WHO target is really 5 micrograms per cubic meter for our annualized average exposure levels for PM 2.5. Now, bringing it home to India, and especially to the capital, which Delhi has been given the dubious title of the world's most polluted capital for nearly 4 years in a row now. There was a recent New York Times article which talked about a waste to energy plant in the center of South Delhi, in Okla. It said in an effort to turn India's trash mountains into energy has become an acute health crisis for 1 million people in the capital city of Delhi. An investigative correspondent has explained what years-long New York Times investigation found. Basically, they did testing of air quality samples and dust samples from around this area, and they found very heavy metal poisoning in the dust and in the air in Delhi. And this wasn't just one sample, this was multiple samples over many years is what they found this to be a reality in our city. So what can one do? What can one do? And I'm going to focus more on case studies over here shortly, but I want to very quickly talk about two main categories of filtration because what's in the air is harmful. It's typically invisible, but it can be filtered, it can be cleaned, it can be measured as well. And how once you measure it and you know what the problem is, the next step is to clean it. And there are two, at a very high level, there are two main categories of air filtration. One, active air filtration, and the other, passive air filtration. Passive filtration been used for many, many years. It's simple sieve filter technology. You have media which will passively filter particles depending on the size of that media, and it will pass through what is, depending on the size of that media, it will pass through what can easily pass through. Or you have sorbents, which are also passive, like activated carbon, which will absorb certain gases and pass through the rest of the air. Active filtration technologies, on the other hand, are more recent developments, perhaps in the last 5, 10, 15 years, with the exception of maybe electrostatic precipitators, which date back a little bit longer, which have typically been used for exhaust systems, but recently been starting to be used for indoor air quality systems as well. So very quickly, passive air filters. What are passive air filters? Media filter for filter particles. So high efficiency particle arrestor is what a HEPA filter typically stands for. They're typically pleated media, but not necessarily all pleated media is HEPA. So just because it's pleated does not mean that it is HEPA. The term HEPA can be used very loosely, so one has to be careful about that. And there are different grades of filters ranging from G1 up to U16, with the G1 to G4, then M5 to M6, then F7 to F9, and then H10 to H14, and then Ultra 15 and 16 and above. So those are the different grades of filters, and HEPA typically is for grades above H11 is typically considered HEPA grade filters. Media filter to filter gases are very important. And here today, I want to talk a little bit more about the gas phase filtration. Particulate matter at a very high level, I'll just break it up into three components. One is the larger particles, which can be filtered typically with the typical filters used in air handling units like the pre-filters or even a G7 grade filter or an F7 grade filter. And then there's the fine particles. So you have the HEPA filter that can be used for fine particles. But now we've got even the nanoparticles. In a city like Delhi, we have CNG, and CNG produces nanoparticles in the air. And for that, you need even more finer filters, the higher grades of HEPA filters, the 13 and the 14 and the 15s perhaps required to remove the nanoparticles from the air. Now, coming to the gases, this is something which is still a very, very less targeted, less known, less talked about problem that we face in our cities in India. The kind of gases that we find in the air are something that I want to talk about. On the next page over here, I have a long list. It's just starting with A and B. And then for each for each letter in the alphabet, we have a long list of certain gases. And there are ways to actually eliminate all of these gases. And we have found many of these list of nearly 250 gases that I have. Many of these have been found. But what are some of the most critical gases that are found in Delhi, especially, or many other parts of India also, perhaps? So the easier ones and that are known more commonly are nitrogen dioxide and sulfur dioxide. These typically come from exhaust fumes of the automobile sector or any kind of combustion activity from industry. The second one is the other gas. The next set of gases that we find a lot in Delhi is the hydrogen sulfide, H2S. We have a lot of open nalas, open sewage systems. The drains are very open. And from those drains, because there's sewage flowing through those open drains sometimes, the hydrogen sulfide comes out, which then corrodes the copper pipes of air conditioners in certain areas. Imagine if it is corroding the copper pipes, what it could be potentially doing to our lungs as well. And then we also have been testing a very high level of chlorine in the air in Delhi. And the chlorine can come from two sources. We burn nearly 7,000 tons of waste in a single day in Delhi, and most of it in the open. So, and we have a lot of plastic in our waste. So when that waste burns and the plastic burns, it releases chlorine in the air, and that is the chlorine that goes in and what we're breathing. And the second source of chlorine is the farm sector, the agriculture sector in India. We burn a lot of our parali, or the husk that comes from rice, and that is also sold to industry, and it is burnt throughout the year. It is not just a seasonal phenomena that where the burning happens for 2 weeks in a year. The husk from the rice paddy is burnt throughout the year because that is considered fuel for small scale industry. And that husk actually has chlorine inside of it because one of the potassium that is needed for our agriculture sector is basically put into the soil in the form of potassium chloride, a liquid, and the chlorine then binds with the agricultural produce, and when it is burnt, gets released into the air, and that's where the very, very high levels of chlorine have been found in the air in northern India, especially. So you have to really focus not just on the particulate matter, PM 2.5 and AQI, but now I think it's time where we start focusing on some of these gases also, because they are creating a huge challenge from a health perspective for us. So we need to start measuring these. We need to start reporting these in a better manner. And of course, we need to have the technologies available for the masses so that we can figure out how to protect them from being impacted from these harmful gases that are present in the air. So there are a list of more than 200 gases that we've tested for refineries, for laboratories, just out in the open. Depending on locations, we found a whole bunch of different ones, and different kinds of gases can be used to actually filter out some of these harmful gases that are different kinds of filters can be used to filter out some of these harmful gases in the air. Now, coming to active air cleaners, I say buyer beware, because some of these technologies can produce byproducts like formaldehyde, like ozone, which can be very harmful to the human body. And there are so many names for these: electrostatic precipitators, photocatalytic oxidation, dry hydrogen peroxide, bipolar ionization, corona discharge, needlepoint oxidation, etc. How do they work? They're typically reactive oxygen species that are released in the air. So they're changing the chemical molecular structure of an air particle. The moment you do that, you may be removing certain harmful aspects from the air, but when you change the molecular structure, the chemical composition, the formula, there will always be some byproducts that will be produced, and you got to be careful of that, like ozone, ozonization, or hydroxyl radicals, or oxidation. So you got to be careful what are the byproducts that are being produced by these, and you just got to make sure you're measuring those and ensuring that you have other technology. As Hannah mentioned earlier, there are special filters to remove the ozone that are produced from that. But when you add those other filters, what is the pressure drop? Is it worth having that electronic filtration with the extra filter for removing ozone? Because then the pressure drop may be as much as a particle filter, perhaps. So these kind of oxidants react with airborne contaminants and everything else in the air to give you the results. The fact is that these are free radicals, or ozone is produced. They're unpredictable reaction as they react with everything in the air, not just the pollutants. And they're unproven to be completely safe or effective as compared to passive media filters. Not a single peer-reviewed scientific journal has any paper published on these technologies. And the question to ask is why? So quickly, I'm going to run through a couple of case studies of actual implementations that we've done for various facilities. So I'm going to talk about the office for Morgan Stanley in Mumbai. They had a big problem, and they came to us and they said, we have a big challenge with regards to gaseous contaminants in two locations. One was their server rooms, where they said their servers are failing more frequently. And being a financial institution where servers failing is not a good sign. It's not good for the bottom line for a company like Morgan Stanley. And also, they said in one of their offices, they found the very peculiar smell coming. They thought it was from the kitchen or from the toilet. They weren't sure because they were close by to that particular office. So we figured out where the source of that was. We closed the source, but some of the odors that had kind of gone into the wall, into the fabric, into the into the carpets was still lingering on for a long time, and they wanted something to fix that problem. So specific gas phase filtration technology was used with particle filtration to ensure that the entire area was eliminated of the harmful odor that they were experiencing. The total area was about 30,000 square feet over 2 floors. The project was commissioned in 2019-20. We've been continuously monitoring the air quality for Reset certified dashboard, and the hotspots for secure and separate Wi-Fi connectivity were created. We used the IQA GC multi-gas air purification unit for a couple of the critical areas like the server room, as well as that particular room where where there was a huge problem with odor. But for the rest of the facility, upgraded the filtration in the air handling units, which ensured that the particulate counts and the gases were under control. Another situation we had was right here in New Delhi, where we are headquartered as Breathe Easy. There was a hospital over here called Sitaram Bhartiya Hospital. They had a huge challenge with stale air and odors in the basement office. The hospital is spread across 3 floors, from the basement to the ground floor and the first floor. And in the basement, they had a lot of the different facilities for the hospital running over there. And because they did not have proper ventilation, a lot of the odors would move from one facility to another through the air conditioning system because of poor ventilation in the basement. And those odors were to the point so harmful that people were complaining that the people in the office who were not going there because of any illness were actually falling ill very frequently. And so the management of the hospital reached out, and they said it's a 7,000 square feet facility. The offices span 2 different floors over just the 7,000 square feet of the office facility. And what can we do to help them improve that air quality? Because that's what they thought was making them sick. They were actually right. That it was the air quality that was making many people sick over there. So we put in a system which brought in fresh air from outside, fresh but dirty air, because very high pollutants of particulate matter and certain gases. We removed all the outdoor pollutants of the PM 2.5s, the ultrafines, and the gases, and we pushed that air and created positive pressurization within that space. Within 6 months of implementing that solution, we started getting data back from the hospital that absenteeism had reduced dramatically within the office, and people were very happy. They did complain about sound because the unit was installed very close to their office, but then we went and did a slight modification after 6 months, and the sound levels also improved, and they've been very happy ever since. So that's another area that you have to be careful of when installing filtration systems, is the sound levels of that system shouldn't travel to the occupied space. We learned that by experience and actually doing something wrong the first time around for that customer. Another quick case study, another finance office called DMI Finance in New Delhi. They were building a new office, but in their existing office, they had a huge problem of mold. So it's a very old building in the ITO area of New Delhi, and that old building, from the walls, there was mold coming in. The builder had put in all this wooden paneling to make it look very fancy, but many people started complaining of moldy odors in the air, and they started to fall sick because mold can give you a lot of allergies and block your sinuses and create a lot of problems. And as the number of problems started to increase, they called us in and they said, what can be done to fix this? And when we saw the problem, we said, hey, you got to remove all of that wooden paneling that has been done, because the mold is now behind this because there was moisture in the walls. We did a complete ozone treatment for mold remediation. We flushed out all of the ozone after that, and then we put in proper filtration within the facilities after fixing the moisture ingress that was there in some of the walls. And today we're monitoring the air quality continuously. It's a Reset certified facility. We've got recirculating filtration systems as well as fresh air systems, removing particulate matter and all the harmful gases coming in from the outside into the facility. The last case study that I want to quickly talk about before we can probably go into Q&A are this is actually data from my own bedroom, and I want to share this because on the left, you see two data charts about on the left, what you see is the CO2 levels. If you see the levels, they would go up to 2,400 parts per million at night when we were sleeping. And this is when I had an air purifier running in the room. So with an air purifier running, my PM 2.5s would come down to about between 10 and 20 micrograms. Still not good enough because I want it close to zero. The World Health Organization says that this should be at 5 micrograms. So with an air purifier running in a small bedroom, about 190 square feet only, and that air purifier was graded for 600 square feet that was running in my bedroom, I was still able to bring it down only to 10, 12, 15 micrograms per cubic meter for PM 2.5. But the CO2, which should be at 800 or below parts per million, was going up to 2,400 parts per million with two people sleeping in that room. Huge problem. So I kept figuring out what to do for this problem. And finally, when I did, I realized that positive pressured air filtration is what is required. And once I did that, by bringing outdoor air and filtering that outdoor air into my space, I was able to bring the CO2 levels down to 700, 600 parts per million all night long. And because of the positive pressure, what happens with the positive air pressure is when I'm pushing clean air into the room, that positive pressure makes clean air leaks out of the bedroom from under the door and the windows. And when that clean air is leaking out, nothing can come in. And hence, inside the room, I'm able to achieve nearly 0 or 1 micrograms per cubic meter of PM 2.5 exposure, which is exactly what I wanted. And now I have this solution running in my entire house, and the entire air quality in the house is between 0 and 5 micrograms for PM 2.5, and the CO2 stays at about 700, 800 parts per million. I'm also measuring the gases in my house because we have very heavy gas filtration because of the kind of gases we've been measuring in the air in Delhi, and we ensure that all the gases are also taken care of. And difficult to measure constantly 24/7, so I don't have good charts, but spot measurements of gases are what we do once in a while in the home to make sure that we are protected and safe from all the harmful gases. So happy to take questions on this. Thank you, Dipanjali, once again.